This instrument is designed and fabricated for meeting reforming under the optical condition with a visible range. And today we will introduce this instrument to be used as for other reactions with gas and steam generation. First, we can see this instrument is designed with three lines. Three gas line was installed with nitrogen, methane, and hydrogen. You can also change the gas follow your experimental design. Nitrogen was used to remove the air inside the system, so you need to charge the nitrogen before you start the experiment. Methane writing in this reactant is the reacting gas. You can replace it with other gas. Follow your experimental design, like carbon dioxide. There is one mass flow controller was installed in this line to supply high accuracy flow rate for the reactant gas. But you can also use it for other gas with the calibration factors. Hydrogen is used for reducing the catalyst. You can use it or not use. It's also dependent on your experimental inquiry. Okay, this is the full of the optical reforming system. We will start from the first gas, hydrogen. Hydrogen, the function of the hydrogen we use to design is for the reduction of your catalyst. So whether you use the hydrogen or not is dependent on your experimental design. Whether you will use hydrogen to reduce your catalyst, to do it into a reduction form or oxidation form. But I think in here will be a little bit difficult for you to do a reduction, because commonly the reduction of the catalyst need a little bit high temperature, right? But in this system, we don't have high temperature being supplied. So initially this hydrogen was installed is for future. For future, if you can install a furnace, then your reforming system become classical reforming. So you can do in high temperature. Then at that moment you can do the reduction of your catalyst. So based on this condition, if the hydrogen was not being used, now you can use the hydrogen line. You can use this line as other function. For example, supply your reactant gas or your mixturing gas. So this is the function of hydrogen. In the original design, this system was used for methane reforming. So the methane gas was installed. But at that moment, the methane was require high accuracy, so a mass flow controller was installed in the methane line. Unless you are using methane, then you can use this mass flow controller. Because this mass flow controller is especially for methane gas. If you use other gas, because the density is different, the thermal property of the gas is also different. So we lost accuracy. But you can also do calibration if you want to use this. You can use soap bubble meter to do the calibration of the mass flow controller. Then find the rate, because the rate is fixed. For example, you supply, then you read the bubble, the real number and your bubble, there will be a rate. Then in future you can follow that rate. But if you use gas other than methane, you cannot use this mass flow controller. For example, if you want to use methane for your carbon dioxide, I recommend you use here. The flow meter is much more accuracy than you to use this one, because you need to do calibration first. If you use carbon dioxide, you connect your carbon dioxide to this line, and you can let the valve to follow the direction of this way. Then your gas will pass through here. And if you use the mass flow controller, you just follow this way, but this you need to close. So,
Yeah.
so this is the original design. They're dependent on which one you are using. You can also see there is in the top is nitrogen was installed. I think nitrogen you will always use because you need to charge the system to remove the air inside the system. And this nitrogen, you can see there is two. This is they have got dual. Previously, this is used in carrying the steam by the high flow nitrogen, but now you are changed into steam generator, so you don't go this line now. But if you use hydrogen, so you will go from here, turn it on, then your line go from here, turn it on, through the flow meter into the system. So. So the first step in your condition, you will run the nitrogen first. You run nitrogen first, go through and pass through your reactor. After you finish the charging, you close your nitrogen. Then you start your steam generator. When your steam was stable, you supply your reactant gas. I think this is basically the procedure of your. And there is also a hydrogen gas line was installed in this system. But commonly the hydrogen was used for reduction the catalysts. However, mostly the reduction of the catalyst will take high temperature. But in this system, there is no furnace was installed. So the hydrogen may not be that useful when your catalyst reduction need high temperature. However, if your catalyst still can be reduced under the room temperature, you can still try to reduce your catalyst in this system. To start the supply of the hydrogen, we will follow the same procedure. Turn on the hydrogen gas to the system and let the valve to pass through the flow meter. Then rotate the flow meter to send it to your required value. However, no matter you use hydrogen or use reactant gas or use the nitrogen, the valves, other valves must be closed when you use other gas, unless you are using mixture gas. So in this system, it allowed you to combine different application. You can supply your reactant gas in pure, or you can make your reactant gas in mixture or be diluted by nitrogen, or be mixed with hydrogen, or be mixed with other gas. This is all dependent on your experimental design. We have sent our standard operation procedure for meeting reforming under optical condition to your student. If you want the standard operation procedure be fit for your new reaction, you can write down your old SOP and send to us for checking. We will review your standard operation procedure and resend back to you after checking. The control panel includes all the control meter in this system. So when you start your reaction, you can turn on the main valve. But when you turn on the main valve, it only indicate the power will turn on, but there will be no electronic supply into the system, because there is also another lock was installed to forbid other for strangers use your system without permission. So every of you, if you want to use this term, you need to got the owner permission and got the lock key to start the system. The controller, including the meter for mass flow controller of the reactant gas, indicator of the pressure, and the temperature program controller, and also the temperature of the reactor, and also the temperature of the cooler. This one now is connected to the cooling system, and the switch is installed, the switch of the light and switch of the cool. This is spare part for program temperature controller, and there's extra spare switch. Initially this system was designed for optical metering reforming, but based on the limitation of this reaction, it may be not got that high activity, because there's scarcely research was conducting under this condition. In case the system need to be conducted under high temperature to be used as a standard reforming reaction, so the system was installed a spare program temperature controller. This one can be used when a furnace was being installed, but recently this system didn't install any furnace, so this one didn't install thermocouple, so it will show with ORAL. You can ignore it, you don't need to worry about it. It's present in this way is because there's no thermocouple was being installed. The pressure indicator is also used as a spare part. In case your reaction will be bear a pressure, but recently because of your limitation budget, this system haven't installed any back pressure valve yet, so the pressure indicator didn't present any valid values. With the installation of a back pressure valve in future, this system can be used as a fixed pressure reactor. To start a reaction, you can take out your reactor, filling your catalyst in, and block both sides with a cotton wool to forbid the escape of your catalyst. After that, you can start the preparation of your reaction. Normal procedure: charge the gas with nitrogen first for maybe 20 to 30 minutes to remove the oxygen inside the system. After that, shut down the nitrogen and change it into reduction gas if your catalyst need to be reduced. Otherwise, you can directly inlet your reactant gas, followed by the line through MFC, or followed by the line through mass flow meter. If you have the steam to be supplied, you can either supply your steam through a steam saturator or a steam generator. To start your reaction, you need to connect your system into the gas. There's 3 gas was installed in this system. Follow the sequence of nitrogen, reactant gas, and hydrogen. Of course, you can use the gas, follow your experimental design, but you need to remember your gas type. This sequence following from the front to the bottom with the same sequence as in the gas line. You can see the gas line. When the gas passes through into the system, it will pass through one of the 3-way valve first. you can lead the three-way valve in this way to let the gas going into the system. This nitrogen can be going in two ways. First way is going into a water saturator to supply the steam. If you use water saturator as the steam supply, you can use this valve to be turned on, and this one turn to vent first to before form stable steam. Then you increase the flow rate to carry enough steam. Follow your experimental design. The dew meter will indicate the real dew. You can transform the dew into the concentration of the steam. This steam supply also can be supplied by a steam generator. If you are not use the nitrogen as a carrying gas, but use as a charging for the system, when you give in the nitrogen supply, and you can turn on the BV3T01 and turn on this valve and turn on this valve, then the gas will supply into the system. You can adjust the flow rate to your predicted value. Follow your experimental design. When you finish the charging, you can turn off the nitrogen supply and turn off all the valves of the nitrogen. The reactant gas include two types of calibration meter. One is mass flow controller, supply high accuracy flow rate. One is flow meter. When your flow rate require higher than 50 milliliter per minute, you can use this flow meter. But when your flow rate below 100 milliliter per minute, you can go through mass flow controller. This mass flow controller was calibrated for methane. If you use it for other kind of gas, you need to do your own calibration to find the effect factor to let the accuracy to be fit for your applicant gas. So when the gas was supplied, you can turn on the BV3T02, let the direction to the system. If you use mass flow controller, you can turn on the gas to the mass flow controller and let it go through the MFC. Then the value of the mass flow controller you can send from MFC stage 4. You can click the direction key to select the position. Then use up and down key to confirm your setting. After you finish your setting, this value will record it, and when the gas was supplied, the gas will controlled based on this setting value. If you use a flow meter, you will not use MFC, so your MFC valve will be closed. Then you will turn on the valve for mass flow meter and rotating the button to control the flow rate to your value. But the limitation of this flow rate meter is it's designed for big value, so it may lose accuracy when your value is low. MFC will supply high accuracy gas when your flow rate is below 50 milliliter per meter. But when your gas flow rate is higher than 50 milliliter per meter, you can use this flow meter to supply the gas. Send the steam generator from here, supply the amount of the steam by the amount of the water by the unit of milliliter per minute. Vent the steam and check about the steam status from this tube. Take care and make sure this tube was put in some container to forbid the burning of yourself. And when the steam was supplied stable and saturated, you can shift the steam to your reactor to start your reaction. You can change your gas flow either by rotating flow meter by rotating, or the reactant gas by mass flow controller. The temperature of the reactor can be observed from here. The temperature of the chiller can be observed from here. You need to turn on the chiller before you start your experiment. This chiller will help you to condense the steam and also can be trapped your product if there's any product flow to the gas liquid separator. A gas liquid separator was installed here. With the cooling of the coil tubes surrounding the gas liquid separator, the liquid will be condensed. And after your finished reaction, you can collect your liquid products from this tube. And during your reaction, you must close this valve to forbid any leaking of your liquid products. Turn the light button on when everything is ready. Then turn on the light through this button. The light will turn on now. Increased intensity by click this button. You can see the light was become much stronger. Measure the light intensity through your intensity meter. Follow the real intensity values when you do your reports. Decrease the intensity by click to lower. After you finish your reaction, you can switch off your light. Collect your sample by this sample pot. Rotate the valve to the sample and put your sample gas bag here to collect your gas sample. Your liquid sample will be collected at the bank of the reactor.